A very interesting twist on the chip-on-board arrangement, the COB LEDs. This one came from eBay, rather predictably, and it's described as one-piece 50-watt hydroponics. DOB, does that mean driver on board? I'm guessing it does. AC, LED, COB. Chip F, grow plant light, full spectrum, loads of keywords and things like that. I ordered a blue one. The reason I ordered the blue one was because I wanted to take a closer look at the LEDs themselves. It comes with this little frame designed to actually allow you to clamp it down without shorting stuff out on the circuit board or damaging it. And it's interesting because it's completely different to the traditional LEDs before the sort of driverless ones that use the separate power supply. And it's a step in the right direction. And that idea of buying this LED to test this was inspired by the teardown of a low voltage lamp that had a really unusual filament, and I'd never seen the LEDs using these before when I looked at them. So before I go any further, I think we should test this. It's a blue one. The reason it's blue is so it's clear gel so we can see the chips. I've got a couple of leads made up here, which I shall now attempt to put into it. I've not tried this yet, so I'm not sure how easy this is going to be. I'm guessing this is the push down system. It beats soldering the wires on. I'm guessing that's a sort of common complaint with the hydroponic posse, because this makes it much easier to terminate the wires when you've got this connector pre-soldered on. Although, I don't think that's supposed to crush down like that and not returned. I've already broken it. Okay, right. That's a good start. Note to others, this is quite easy to break. Let's get that out of the way. And we'll see if I can recover from this. I'm not sure if I can recover from this. Push this down. Yeah, this is where a little interlude would have been quite handy. That wire is just not going to stay in there. Right, one moment, please. Okay, yeah, I've completely broken that, so I've mushed the wires in a non-compliant manner that hopefully they'll stay put. On a plus note, you could heat this on a panel. These things, if you want to solder onto them, because they've got the aluminium core at the back, it makes them absorb heat away from the solder joints, but it does have the live and neutral pads here, so if you do what I've just done and just press that little thing down, then it makes loud crunching noise and never works again, then there is another option. So let's test this. I've not got this in a heatsink yet, so I'm not going to run it for too long. So let's get the hoppy in and annoy you all with a flickery display. And let's get the Cliff Quick test. I want to do two things here. I want to just make it light up just to see it is working. It may not be working, who knows. It may go bang. That would be very exciting and worthy of videoing. So I've got the Cliff Quick test here. I'm just going to pop the wires in. And then I want to actually try it with the resistor in series. So this is going to get very bright. I shall plug this into the hoppy and then close this lid down. Oh, it's very bright. Yeah, that is. And flickery. And that is an important thing here. It's very flickery. Let's let that cool for a second. Then let's look at the readings here, which I should have done in the first place. 33 watts, 0.9 power factor, which is pretty typical. Yep, that. And as it heats up, the chips, the whole metal plate will get warm and the power will go down. Now I want to stick a resistor in series of this purely because that will let me see how well matched the LEDs are, or if there's any that are sort of shorted out. So let's stick a 1 megohm resistor in series. The current won't even register on this now. It may show visibly. It's not even glowing. That I'm going to require a bit more. There's obviously, of course, there's enough of a load in that circuitry. One moment, please. Okay, with a 220k resistor in series, they all light very evenly. At low intensity, the power is 0.5 of a watt at the moment. So you can tame these down by putting resistors or, I suppose, a capacitor in series. The circuitry, let's take a closer look at the circuitry though. That's what we're really interested in here. I'll get these wires out, if I can get this wire out now, because the blue one should hopefully just pull out. Yes. Does the brown one pull out? No, it does actually require that to be pressed down in a more delicate manner than I did it. There we go. It appears that just using subtlety works and not super full-on bare strength. Excellent. I'll just tuck these bits out of the way and then bring in some more exhibits in terms of pictures that I've already taken this already. So, for reference, here is a blue chip, which is the sort of lower voltage one. This one has shit LEDs in it. And if we take a look at this one, here's a picture I took earlier. You can see the bus bar down the side, and then you can see the gold bond wires jumping onto each chip. It jumps onto a pad at one end of the chip and off at the other. Now, if I bring in the listing here and fold this over, just because it's the closest bit of paper to hand to doodle on, and I grab a pen to doodle on, then looking at what I'm seeing here, the chips look like this. The LEDs are a rectangle that has been bonded onto the back plate, and they have a pad for the gold wire to bond onto, one at each end, and the one at that end has a little electrode going out like that, and the other ones have a little electrode going out like that. And I'm guessing these electrodes may not be in the same level, because these tend to be done as layers, these chips. But the idea is that you can see the wire comes on, the bond wire comes onto here, and it bounces off, and then it's bridged right over to the next LED. And it just continues all the way across and onto the end. Now, the end, keep in mind that these have to be almost like a micro spot welded on, and it's quite a laborious job. It's semi-automated, but a lot of it is manual. And when it gets to the end, the same spot welder is used to try and tack the leads on. Well, I can tell you, when I power this up and just squeeze the ends, it makes a bad connection. And quite often, one of the failure modes of these LEDs is losing whole lines of LEDs. And if, while it's powered with a suitable safe low voltage, or if you're using an insulated thing, if you poke the wire where it goes onto the bus bar, quite often that strip of LEDs will light again. Note the lovely image of the ring light I was using to get these nice clear pictures. Also notice all the lint. This LED was very dusty, and I washed it with soap and water, as one does with LEDs. And then I foolishly after that, because this silicone type stuff is sticky, I wiped it with tissue, and unfortunately all the lint, so that's all the little strands. But you've got the gist that all the bond wires are going across, and it is quite laborious and complicated putting those bond wires on. Here is the chip we're looking at the moment, and it has 0 bond wires. And if you take a closer look at the LEDs, you see that there's not even bond wires locally in them. They appear to be almost soldered in, almost like tiny surface mount chips. And if you take an even closer look, and the magnification here is ridiculous. To get this, I had to basically I had to light this well and hold the magnifying glass in the microscope in front of the camera to try and then line them up and focus and get a picture. I kind of got a picture. But what we can see here is that the outline of the chip here goes onto the pads, which are these things here. And there's a very obvious layer of solder going here. So these LED chips, these bare emitters, have just been soldered onto these pads, which is incredible. I would say I've never come across this before. I came across it in this thing, but I didn't realise how widespread it was. And suddenly, the reason the market is flooded with these COB LEDs makes sense. And there is an obvious pattern. There's a sort of purpley one here, and a purpley one here, and a purpley one here, and a purpley one here, and then a purple line here. And I'm guessing the colour is affected by the layer they're on. And I'm guessing that these might be coupling down to the sort of solder layer. Not sure. But then there's another electrode, a little round pad here, and then the other electrode comes along here. So we've got our 3 electrodes again, much like we had with the gold bonded one. But this time, I should actually draw them as wider. They're actually a lot wider than that. They're actually quite modest strips. But this time, instead of actually having a gold wire bonded onto them, they are, I guess these might be some kind of the equivalent of a plated through hole through the semiconductor LED to some sort of metallization at the bottom. And it really does look like solder. So it looks as though they've perhaps pick and place these at some micro level, because they are absolutely tiny, and then just flow soldered them with the rest of the chip. That's incredible. It makes it so much less complicated to actually make these. Other things worthy of note here. Here's the mains coming in on this connector that is apparently easily broken if I try to operate it. The next thing in line is quite commonly used in these. It's always a good idea to have these. These are metal oxide varistors, and the idea is that if the voltage exceeds a certain threshold, if there's a spike, instead of it affecting the circuitry and potentially causing quite a high current pulse or damage, causing an avalanche effect that could actually cause the transistor to basically turn on continuously and blow all the LEDs. This thing is here to protect against that. It clips any voltage spikes by going low resistance when a certain voltage threshold is exceeded. In this case, it says 471. That means 47 and at 10 at the end, so 470 volts, it'll actually turn on to protect. So kind of have a sort of curve in that area. Then we get the bridge rectifier. So we get the AC going in, I'm guessing, without actually scraping that off, I'm guessing that that's AC at that side, could be wrong, and then the DC coming out this side. The connections then go. There is one pad that I can see a ghost of actually coming. It comes out as a wee track from there, and then it fans out. And I think the reason it fans out is because these LEDs are wired as parallel pairs across the circuit board. And that track then seems to continue underneath the edge there. I guess they've kept it well in away from the edge because there's going to be hardware mounted here. And then it goes to the circuitry. There's another track coming up and going to this empty resistor position, and that empty resistor position happens to go into the middle of the LEDs. You can probably work out what's happening here, particularly when there's one 0 ohm link going in here and it's connected there, and I can see a track coming up there, and this one is probably connected to there. And the output from the LEDs is a fairly fat track here, and it's coming across over to the transistor here. Plus, again, there's a connection coming up, and it's basically skimming along the edge there, curving around that hole, and then going to the circuitry. So my guess is that since there are 144 LEDs, it's 12 LEDs by 12. That is a lot of LEDs. If they were all wired in series, then the voltage required to light them would be a 144 LEDs times 3 volts each. So 432 volts, that's not even going to light and peak UK voltage. So if it's 144 LEDs and they're wired as parallel pairs divided by 2 equals 72 LEDs times 3, suddenly that comes 260 volts, comes well within the range of the 222 40 volts. The flicker is caused because there's no smoothing, which is unfortunate here. That it is down to the fact that, it's the simplest circuitry. It's using that current regulation based on a chip here and a transistor to limit the current resistively effectively through the LEDs. Now, the reason for these links is that if you put one here, it's almost like a transformer with the secondary windings. It connects 2 sections of LEDs in series, and that means that all the LEDs, those, 144 divided by 2 equals, so the 72 pairs of LEDs are all in series. But if you actually remove that link, I'm guessing, and put a link here and here, then it connects them in parallel. So this is one feed from there going up to the middle, and one feed from here being branched down to the other end. So effectively, it creates 2 parallel clusters. And now, that would be the equivalent of 144 LEDs divided by 4, 36 pairs in that section, and 36 pairs in this section, all connect in parallel, and they are going to require about, say, 108 volts. So that's the 110, 120 volt option. So if you've been supplied one of these and it's got the wrong voltage option, if it's just got that one link, it's probably been set for 240, and if you want to correct that, you can remove that link and just link over these 2 outer ones, and that should theoretically set it to 110 volt. The circuitry here, I looked for the chip numbers. This transistor is called a SH180824060, which manages to only pull up one link to some Facebook page. It's nothing. It's just, it pulled up a random coincidence number, I think. The chip here says 1089B, and underneath it says 1831. Given how new this is, the date is 24th day, 7th month, 2018. I'm guessing that's a date code, 31st week of 2018. So 1089B, I drew a blank on that. But let's deduce what's probably going on here. This will be monitoring the current through I guess these resistors. There's 3 identical resistors, 24RO, 24 ohms, and I'm guessing, I've not measured this, that they are probably in parallel, giving a total of 8 ohms, although I could be wrong. Let's bring a meter in and measure that. Let's just poke it right through the gel. This is all covered in gel. To read these numbers, I had to scrub the gel off. So let's probe through to there, probe through to there. What am I going to get? 8 ohms. They are all in parallel. So they are the current sense resistor that will be providing let's put the meter out of the way and not the LED. They will be providing the feedback to, I'm guessing, this chip. The Zener diode is possibly a power supply reference for that chip. And there'll just be, to give it its low current supply, there'll be one of these resistors. This is 560k. This is 180k, I'm guessing. One of these is probably being used as a power supply for that chip, just to limit the current to it, and then it's probably capped by the Zener to stop the voltage going up too high. And then the others will be just perhaps, I guess the capacitors would be for stability. These resistors here, not quite sure they'll be for. Maybe they'll be for fault detection functionality. But the gist is that when the current exceeds a certain level through the LEDs, the voltage across these resistors will be high enough to actually start turning this transistor off, and it will then limit the current. It might all just be based on a discrete transistor arrangement. This might purely be a management chip, but the reason that they've not got any numbers that are obvious, I don't know if there's data sheets out there for them at all, or is it just one of these things that either, it's abbreviated number, I didn't find the full number, or is it because it's such a specialised and recent chip just dedicated to these high output but compact driver on-board type LEDs, that they're just aimed strictly at the manufacturers at the moment. There may not even be data sheets and free availability for them yet. But that's very interesting. That is a very interesting LED. What else is there to say about this that's worth mentioning? It says T4050. I'm guessing that just does 40 or 50 watt. The LEDs are tiny, but having said that, there's a lot of them to spread the load over. I do prefer it if they underrun LEDs. I suppose that really if you wanted to do that, if you wanted to make them last longer, you could ultimately change the value of these resistors to a higher value effectively, so that the voltage threshold was reached sooner at a lower current. Other things worthy of note. Yes, the hydroponic posse have been getting very adventurous with these driverless chips because they're so cheap and easy to get. I've seen some exciting videos on YouTube of people who have made large panels of them. They've got a metal panel in their lap, and they're kind of propping up in their lap, and there's no obvious earth connection, and they've got 2 meter leads, and one is neutral and one is 240 volts straight off the mains, and they're probing around testing their LEDs on the panel like this, and it's like, oh shit, for fuck's sake, don't do that. It's not the safest thing to do, particularly when you've got the metal in your lap and you're sitting down and there's Anyway, it's worth mentioning that some people seem to think these don't need earthed. If you've got this metal plate in a heatsink, although there's a shim of fiberglass circuit board, it really is just absolutely minusculely thin. To the point, let's see if I can even feel this. There's a little hole through that there. It just feels almost like a piece of sellotape stuck. That is probably just the pad though, isn't it? Can I see how thick this is? Is there any easy way to test that? What if I use a little magnifying glass on the edge? It's just wafer thin. It's tiny. I can't even tell how thick that is. But it is very thin. And there have already been reports of metal reflectors coming live because an LED fails and burns. And when it burns, it actually burns through the fiberglass and creates a conductive path to the aluminium. So if you are making large panels of these, I strongly recommend that the panel is earthed just for safety, so it can basically avoid giving you electric shock. This does make you think of someone who recently contacted me and said they'd had two hydroponic lights sitting next to each other and they touched and there was a loud bang and one of them died and there was a big skid mark where it had touched the other one. One was earthed, the other wasn't earthed, its case had been live at mains voltage. Exciting. So there you go. Interesting. I wonder how these are going to evolve. They are so tiny. The failure mode of the other ones tend to be the bond wire. Is this going to solve that problem? Is this going to make them more reliable? They're so cheap it does make you suspicious. But then again, theoretically, everything can be done with the silk-screened solder paste and then basically pick and place for all the little LED, the bare LED chips as well. It's very interesting. I wonder how they arrange the orientation of that, or even how they pick them up. It'd be interesting seeing the machine that's doing this, but it's so new that I guess there's probably not going to be much video footage of that about because they'll be protecting their technology. But there we go. That's a very interesting twist for LEDs, that they've got rid of those gold bond wires and they are basically just relying on them being simple solder on components now. It'll be very interesting to see how long they last.